Welcome back to QHSE Talks. Usually, when we look at industrial hazards, we kind of expect a certain level of, visibility.
Right, like a missing guardrail on a mezzanine is pretty obvious.
Exactly. Or a puddle of hydraulic fluid on the shop floor catching the overhead lights.
Yeah.
You can point to those issues and just engineer an immediate physical solution right then and there.
Yeah, but as we tackle ASP Blueprint Domain 2, Topic 6 today, which is implementing hazardous energy control programs, we're stepping into an environment where the most lethal threats are completely invisible.
And that invisibility is exactly why this is such a critical mission for today's QHSE Talks. Whether you're an aspiring associate safety professional finalizing your exam prep, or maybe you're a veteran safety manager auditing your facility, mastering energy control is just foundational.
It really is. I mean, it goes so far beyond that iconic image of a red padlock hanging on a circuit breaker.
Yeah, that's what everyone pictures, right? Just the padlock.
Right. But we are looking at a deeply integrated system here. It involves physics, hardware engineering, this really rigid procedural architecture, and honestly, the complexities of human behavioral psychology.
So we have to analyze every single layer of that architecture, because a failure at any one point, like a misunderstanding of the physics or a procedural deviation, that's where incidents occur.
Exactly. And the OSHA standard, 29 CFR 1910.147, it defines the stakes with absolute precision. We're managing the unexpected energization, startup, or release of stored energy during servicing or maintenance.
And the critical variable in that entire definition is the word unexpected, right?
Yes, absolutely. Because the operator running the equipment during normal production, they fully expect the machine to cycle. They're standing safely at the control panel.
Right, they're outside the machine guarding. But when a maintenance technician has to bypass those guards to, say, clear a jam or replace a drive belt, they are putting their body directly into the line of fire.
And if the machine cycles at that exact moment, the outcome is catastrophic. So to prevent that, we have to completely rethink our definition of what energy actually is in an industrial setting.
I think the default assumption for most of you listening, or really anyone, is to equate energy strictly with electricity.
Yeah, you pull the disconnect, the copper contacts separate, the electrons stop flowing, and, the hazard is theoretically neutralized.
But the OSHA standards and the source materials we have for this session require us to expand that mental model a lot. Hazardous energy encompasses electrical, sure, but also mechanical, hydraulic, pneumatic, chemical, thermal, kinetic, magnetic, and even radioactive sources.
Wow. Yeah, that's a massive list.
Yeah.
And we really need to dissect the physics of those specific energy types. Because shutting off the main electrical feed, that only addresses what we call active energy.
Active energy being the power currently driving the system from, the external grid, right?
Exactly. But stored or residual energy is what remains trapped inside the local system's architecture long after that primary umbilical cord is cut.
Okay, so let's unpack that. I think a perfect illustration of this is pneumatic energy.
Oh, definitely. A lot of industrial systems use compressed air to drive actuators or cylinders. And unlike water or hydraulic fluid, air is highly compressible.
Right, so it acts like this giant invisible mechanical spring.
Exactly. So if a technician shuts off the electrical power to the main air compressor, what have they actually done?
They've only stopped the generation of new compressed air.
Right. The downstream lines, the accumulators, the closed valves, they're all still packing air at, maybe 120 pounds per square inch.
So if a worker just puts a wrench to a pneumatic fitting and cracks it open without systematically bleeding the pressure first, that invisible spring decompresses instantly.
And the force of that air can blow the fitting apart, turning a brass coupling into shrapnel, basically. Or it causes a loose hose to whip around violently.
That's terrifying. And magnetic and kinetic energy operate on somewhat similar deceptive principles, don't they?
Yeah, they do. Think about a massive industrial motor or a centrifuge. You cut the electrical supply, but you still have this internal rotor weighing several tons spinning at high RPMs.
Oh, right. The kinetic energy bound up in that momentum. That doesn't just stop immediately.
No, it can take 20 or 30 minutes to naturally dissipate. So if a worker opens an access panel prematurely, the internal components are still a fatal hazard.
And what about the magnetic side of things?
Well, large motors can retain induced magnetic fields. Even without active current flowing, the residual magnetism can be strong enough to cause heavy components to unexpectedly snap together, potentially crushing fingers or hands.
Wow. Okay, so moving down the list, hydraulic systems introduce a whole other layer of complexity, right?
Oh, absolutely. With hydraulics, we are dealing with non-compressible fluids under intense pressure, often exceeding like 3,000 psi.
Just massive force used to articulate heavy machinery. And turning off the hydraulic pump's motor just leaves all that fluid locked inside miles of steel tubing.
Right, it's trapped, and the pressure in those lines is constantly seeking an avenue of escape.
So a microscopic pinhole leak or a fitting loosened by a technician who assumes the system is dead that can result in a high-pressure fluid injection.
Yeah, and hydraulic fluid forced through the skin, that acts as both a blunt force trauma and a highly toxic chemical exposure. It often requires extensive surgical debridement or even amputation.
Which is just awful.
Yeah.
So managing hydraulic energy requires physically opening bleed valves to route that trapped fluid back to the main reservoir, right?
Exactly. You have to completely zero out the system pressure. You can't just flip a switch.
Okay, so then we have potential mechanical energy, which is basically just gravity waiting for permission to act.
That's a great way to put it. Our source texts specifically bring up die-changing operations in heavy stamping presses for this one.
Right, the upper die of a press can weigh thousands of pounds. When the electrical power is cut, that massive block of steel might just be suspended in the air.
Yeah, held up only by a mechanical brake or maybe a column of trapped hydraulic fluid, but gravity exerts a continuous active force.
So if the hydraulic pressure slowly bleeds past a worn seal, or if that mechanical brake slips even a little bit, that potential mechanical energy instantly converts to kinetic energy.
And that brings the die crashing down on whatever or whoever is beneath it.
Which is why the standard mandates a physical intervention for this, specifically the insertion of a die prop or a safety block.
Exactly. A solid load-bearing pillar that's engineered to physically withstand the entire weight of the die, placed right between the upper and lower platens.
So looking at all this, the process of isolating these various forms of energy, it really cannot be left to a technician's intuition or their memory.
Absolutely not. I mean, a complex manufacturing line might have a dozen electrical disconnects, pneumatic dumps, and hydraulic bleeders scattered all over a massive footprint.
And that drives the absolute necessity of the written energy control procedure mandated by OSHA's 1910.147 standard.
Right. The written program is the bedrock of compliance here. It establishes a highly rigid framework. The standard demands that these procedures specifically outline the scope, purpose, authorization, rules, and techniques.
So it's not enough to simply have a piece of paper that says, ensure the machine is de-energized.
Oh, not at all. We can view the written LOTO procedure much like a software architecture for a critical operating system.
I like that analogy. Like, you can't run a generic script on highly specialized, custom-built hardware and expect it to execute safely. Every single node, every physical switch has to be explicitly mapped.
Exactly. The text requires specific procedural steps for shutting down, isolating, blocking, and securing machines.
And those four terms, they aren't just synonyms, right? They represent a deliberate sequence of escalating control.
Yeah, let's break them down. Shutting down is just the initial operational command, like hitting the stop button to bring the machine to a normal halt.
Okay, and isolating.
Isolating requires physically disconnecting the machine from its energy sources, so throwing the main electrical disconnect switch.
Got it. And then blocking involves the physical interventions we just discussed, like inserting the die prop or maybe chaining a heavy valve close.
Exactly. And finally, securing is the actual application of the padlock itself to the isolating device.
Right. And the procedure also has to detail the placement, removal, and transfer of lockout devices.
Yes, and that transfer aspect is a massive operational choke point in a lot of facilities.
Oh, for sure. Like, imagine a maintenance technician locks out a conveyor system at the end of their shift, but the repair just isn't finished yet.
Right, so they go home and they naturally take the key to their lock with them.
Then the next shift comes in to resume the work, and the energy isolation device is secured by an absent employee's lock. What happens then?
Well, cutting a lock off an energy isolation device is one of the most critical, highly hazardous administrative actions you can take in a facility.
So the written procedure must outline a flawless verification protocol before anyone even touches a pair of bolt cutters.
Yes. Management has to definitively verify the employee is not in the facility. They have to make all reasonable efforts to contact them by phone.
And they have to ensure that the employee is explicitly informed that their lock was removed before they ever step foot back on the factory floor the next day.
Exactly. Because if you fail to execute that sequence perfectly, you invite a scenario where an employee returns, assumes their lock is still protecting them, and enters a live machine.
That gives me chills just thinking about it. And that leads directly into the final mandatory element of the written procedure, which is specific requirements for testing a machine to verify the effectiveness of the lockout.
Right. The industry often uses the phrase lockout, tagout, tryout. That tryout verification step is the ultimate safeguard.
It's the safeguard against what? Mislabeled equipment, cross-wiring, faulty disconnect switches.
All of the above. I mean, think about it. A facility might have a wall of 20 identical electrical disconnects.
Yeah, and the label for breaker A might have faded over time, or some contractor rerouted the wiring 5 years ago and just never updated the schematics.
Exactly. So a technician applies their lock to what they truly believe is the correct disconnect. But if they bypass the verification step, if they don't return to the local control panel and attempt to start the machine, they are betting their life on an untested assumption.
They absolutely must push that start button and confirm the machine remains dead.
Yes. And verification of electrical isolation requires a deeper understanding of electrical principles, which actually bridges Domain 2, Topic 6, with broader electrical safety concepts in the ASP blueprint.
Right. Our sources reference OSHA 1926.950, which deals with power transmission and distribution. And the overarching rule there is that all electrical equipment is considered energized until determined otherwise by testing.
Exactly. Pushing the start button is sufficient for mechanical verification, but if a technician is actually opening an electrical panel to work on the raw wiring, they have to physically test the circuits using a multimeter.
And this introduces the required three-point test, doesn't it?
It does. First, they have to test the meter on a known live circuit to prove the meter itself is actually functioning.
Right, because if the meter is broken and reads 0, you might think the line is dead when it's not.
Exactly. Second, they test the locked out circuit phase to phase and phase to ground to prove it is genuinely de-energized.
Okay, and the third step.
Finally, they test the meter again on that known live circuit from step 1, just to prove the meter didn't magically fail during the testing process.
That is so rigorous, but it makes perfect sense. So, because these procedures are so equipment-specific, an initial comprehensive equipment assessment has to be conducted for every single piece of machinery.
Yeah, safety professionals basically have to play detective. They trace the pneumatic drops, trace the hydraulic lines all the way back to their manifolds, and identify the main electrical feeds.
And they document exactly how to neutralize every single one of those sources in the written program.
Right. But having documented the procedure, the actual execution relies entirely on the hardware.
This is a huge point. We need to clearly define the difference between an energy isolating device and a control circuit.
Yes, the text is completely unambiguous here. An energy isolating device is a mechanical device that physically prevents the transmission or release of energy.
So we're talking about manually operated electrical circuit breakers, disconnect switches, line valves, things like that.
Exactly. And the text explicitly excludes push buttons, selector switches, and other control circuit type devices.
So if I'm at a CNC lathe and I hit that massive red emergency stop button, that is legally and physically invalid as an energy isolating device.
Completely invalid. And the distinction lies in physics versus software.
Okay, explain that, because I think a lot of people assume that e-stop is the ultimate safety switch.
Well, an emergency stop button or a selector switch on a pendant, that's just a component of a low voltage control circuit. It sends a digital signal to a programmable logic controller, a PLC, or a relay, essentially asking the system to drop the main power contactors.
Right, it's asking permission. And control circuits are incredibly vulnerable to environmental and systemic failures.
Precisely. A power surge can physically weld the contacts of a relay together. If that happens, it freezes the relay in the closed, energized position, regardless of what the PLC commands.
Wow. Or, a frayed wire inside the pending cable can create a short circuit that just bypasses the stop button entirely.
Yeah, or even firmware bugs or logic loops in the PLC can trigger an unexpected startup sequence. When you rely on a control circuit for lockout, you are placing a worker's life in the hands of fragile microelectronics and lines of code.
But an energy isolating device bypasses that logic entirely. When you throw a heavy mechanical disconnect switch, you physically separate the copper blades by an air gap of several inches.
Exactly. Or closing a mechanical line valve places a solid disc of steel across the flow path of a pipe. We are replacing the software's permission with the immutable laws of physics.
That is such a vital distinction for passing the ASP exam and just keeping people alive. And the hardware used to secure those isolating devices has to meet strict criteria too, right?
Yeah, the text dictates the isolating device must have a hasp, a means of attachment, or a built-in locking mechanism that allows a lock to be affixed without dismantling the device.
Because a safety standard shouldn't require a technician to disassemble a breaker panel with hand tools just to figure out how to isolate it.
Right. That defeats the purpose. And the lockout devices themselves, the padlocks, the hasps, the valve covers, they have to be standardized within the facility.
Standardized in terms of color, shape, or size, right?
Yes, and they must be singular in purpose. A technician's red lockout padlock absolutely cannot be used to secure their personal toolbox or lock their locker in the break room.
Oh, I see. Because when a standardized LOTO lock is applied to a machine, its presence needs to universally communicate a single critical message.
Exactly. A human life is currently dependent on this isolation.
So we've focused really heavily on lockout, but the standards acronym is LOTO, which stands for Lockout, Tagout.
Yes, and exploring the Tagout portion of the standard reveals what basically amounts to a legacy-driven administrative workaround.
Yeah, let's get into this because the text defines a Tagout device as a prominent warning device, securely fastened to an energy isolating device, indicating that the equipment may not be operated until the tag is removed.
Right, but a tag is fundamentally just a piece of plastic or heavy-duty paper. The source text makes the distinction painfully clear here. Tags provide a warning, but they do not provide the physical restraint that a lock does.
Which means they offer absolute zero mechanical resistance to someone attempting to re-energize the system.
None at all.
So if a tag relies entirely on the behavioral compliance of whoever happens to look at it, allowing its use seems completely contrary to the rigorous mechanical standards we've been discussing for the last half hour. Why is it even allowed?
It's a great question. The allowance exists primarily as a grandfather clause for older legacy equipment where the energy isolating device physically cannot accept a padlock.
Ah, okay. So in older, heavy industrial environments, you frequently encounter these massive, decades-old isolation valves or archaic electrical disconnects that just lack any hasp, hole, or geometry to attach a lock or a chain.
Exactly. OSHA recognized the impossibility of retrofitting every single piece of mid-century infrastructure overnight, so they permit tagout systems under a very specific and highly burdened condition.
And that burden of proof is immense, isn't it? If an employer uses a tagout system, they must demonstrate that the tagout program provides a level of safety equivalent to that obtained by using a lockout program.
Right. And achieving mechanical equivalency using an administrative warning tag, that requires a flawless layering of additional preventative measures.
What does that look like in practice? How do you make a piece of paper equivalent to a steel padlock?
Well, technicians have to take steps that physically impede the re-energization process beyond just hanging the tag. This might involve, say, racking a medium voltage breaker entirely out of its cubicle.
Oh, so physically pulling it apart.
Yeah, or completely removing the fuses from a disconnect box and putting them in their pocket, or installing what's called a blind flange, a solid steel plate between two pipe flanges to positively blank off a chemical flow.
Okay, so you're still relying on physics, just taking the equipment apart instead of locking a switch. And the tags themselves are highly regulated too, right?
Very. They must be legible, standardized in print and format, and capable of withstanding the environmental conditions of the facility.
So if they are in extreme humidity or exposed to corrosive chemicals or UV exposure, they can't just melt or fade away.
Exactly. Furthermore, they have to be attached with a non-reusable device capable of withstanding at least 50 pounds of pull force.
Which is typically a heavy-duty nylon cable tie, right? A zip tie?
Yes. But remember, the structural integrity of the zip tie only ensures the tag doesn't accidentally fall off.
Right. The actual safety derived from a tagout system rests entirely on the culture and training of the workforce. If an employee decides to just pull out a pocket knife, cut the zip tie, and throw the switch, there is absolutely no mechanical failsafe to stop them.
Which is exactly why we need to talk about the human element of hazardous energy control. Because the most perfectly engineered physical lockout system fails instantly if a worker just circumvents it.
Yes, let's dive into that. To manage this behavioral variable, the LOTO standard segments the workforce into two distinct categories, demanding specific, targeted training for each.
Right. The authorized employee and the affected employee.
So the authorized employee is the individual actively applying the lockout device and performing the invasive maintenance. They are the ones actually placing their hands inside the mechanical danger zones.
Yes, and their training requirements are deeply technical. They have to be educated in the recognition of applicable hazardous energy sources, the type and magnitude of the energy available, and the specific methods necessary for isolation and control.
So the authorized worker needs to know that the blue pipe holding argon gas operates at 50 psi, while the adjacent braided steel hose holds hydraulic fluid at 2,000 psi.
Exactly, and they must understand the exact mechanical sequence to bleed the accumulators for both.
But the affected employee represents a completely different risk profile.
Right. The affected employee is an individual whose job requires them to operate the equipment being serviced, or whose job just requires them to work in the immediate area.
This could be the CNC operator, the forklift driver bringing raw materials to the line, or even the sanitation worker cleaning the adjacent aisles.
Exactly. And their training is much less about the mechanics of the energy and much more about the sanctity of the administrative boundaries.
They must be instructed in the purpose of the energy control procedure and, crucially, about the absolute prohibition against attempting to restart or re-energize equipment that is locked or tagged out.
Viewing this through the lens of human performance principles, the separation of these roles combats some really dangerous cognitive heuristics.
Like the fact that humans naturally seek efficiency.
Yes. If an affected operator returns from a lunch break and finds their machine sitting idle with a padlock on the breaker, their operational drive is to resume production.
Right, they have quotas to meet. If they lack rigorous training, they might rationalize that the maintenance technician simply forgot to remove the lock after finishing a repair.
Exactly. The operator assumes the repair is complete, grabs a set of bolt cutters, removes the lock, and starts the line.
Completely unaware that an authorized technician is still physically inside the lower housing of the machine, inspecting a drive shaft.
It happens far too often. Establishing this authorized versus affected dynamic acts as a behavioral firewall against those fatal assumptions.
The affected worker has to be trained to view the lock as an impenetrable barrier, not an inconvenience.
Right. The safety management concepts from our sources really emphasize that you cannot engineer out every single human error. You have to enforce an operational culture where the normalization of deviance is actively suppressed.
The normalization of deviance, that is such a powerful phrase. It's where cutting corners without negative consequence slowly becomes the accepted standard operating procedure.
And it is a constant threat to LOTO programs. A technician might realize that skipping the tryout verification step saves them, 5 minutes per lockout.
And after doing it 50 times without any incident, skipping the verification just becomes their new normal.
Exactly. So OSHA combats this erosion of procedural integrity through the mandate for periodic inspections.
Right. Employers must conduct formal, documented inspections of their energy control procedures at least annually.
And the brilliance of this requirement really lies in the specific criteria for who the inspector has to be.
Yeah, this was a massive aha moment for me when reviewing the practice questions in the text. The text mandates that the inspection must be performed by an authorized employee other than the person utilizing the energy control procedure being inspected.
The other than rule. It essentially mandates independent peer review.
Because a technician cannot grade their own execution.
Right. If their routine incorporates a dangerous deviation like skipping the tryout step, they are blind to it. It's just normal to them.
So an independent authorized employee, someone who intimately understands the specific equipment and the written procedure, has to physically observe the technician performing the lockout sequence in real time.
Yes. And the observer is verifying two distinct elements here. First, they are ensuring the technician is adhering to the established procedure without skipping any steps.
Okay, and the second element?
Second, they are evaluating the procedure itself. Over the course of a year, the equipment might have been modified. A new pneumatic line might have been added by a contractor.
So the observer checks if the written procedure still accurately reflects the physical reality of the machine today.
Exactly. And the accountability for all of this must be cemented through strict record keeping.
Right. The resulting certification has to identify the specific machine, the date of the inspection, the employees included in the review, and the name of the person performing the inspection.
Because in the event of an OSHA audit, or worse, a post-incident investigation, this documentation is the primary evidence that the safety management system was actively maintained.
So we've established this incredibly rigid framework. written procedures, standardized hardware, verification protocols, role-specific training, and annual peer reviews.
Yes, it's a lot.
But industrial environments are highly varied, and applying this massive administrative burden to every single maintenance task is just operationally paralyzing.
Right. And the standard authors understood this, which is why they established specific exemptions and edge cases.
So the standard provides an exemption where a formal written procedure is not required, provided the task meets a highly restrictive set of conditions.
And the threshold here is absolute. An employer must meet every single criterion on the list, not just a majority of them.
Okay, reviewing the criteria. The machine must have no potential for stored or residual energy. It must have a single energy source that can be readily identified and isolated. Locking out that single source must completely de-energize the equipment. The lock must be under the exclusive control of the authorized employee. The work must not create hazards for other employees, and there must be no facility history of accidents involving this equipment during servicing. That is a tight list.
Very tight. But the classic application of this exemption is cord and plug connected equipment.
So if I have an industrial drill press or a bandsaw that just operates on a single 220-volt plug, if a technician needs to change the drill bit or the saw blade, the energy isolation requires simply unplugging the machine from the wall.
Exactly, because there are no internal pneumatic lines, no hidden hydraulic accumulators, and no massive flywheels retaining kinetic energy. The act of pulling the plug completely zeroes out the machine.
And furthermore, if the technician keeps that plug within their line of sight and under their exclusive physical control while their hands are near the blade, the risk of unexpected energization by a third party is completely eliminated.
Yes. The physical reality of that setup inherently satisfies the intent of the standard, without the need for a bureaucratic, written roadmap.
That makes total sense.
Yeah.
But while the cord and plug exemption simplifies basic maintenance, the text also introduces edge cases that represent the absolute pinnacle of complex hazardous energy management.
Oh, you're talking about hot taps.
Yes.
Okay.
A hot tap is defined as a procedure involving welding on a piece of equipment under pressure to install connections or appurtenances. This just completely blew my mind.
It's intense.
Because it completely inverts the foundational premise of LOTO. Instead of isolating and bleeding the energy, you are intentionally applying an extreme thermal heat source, an electric arc welder, directly to a pipe that is actively containing highly pressurized, potentially flammable or toxic chemicals.
Right. The physics and metallurgy involved in a hot tap are staggering. You are melting the outer wall of a steel pipe while the internal fluid continues to flow at high velocity.
And if the heat input isn't perfectly calibrated, the pressure inside the pipe can blow out the molten weld pool, resulting in a catastrophic explosion or chemical release.
Exactly. So OSHA permits this extreme deviation only when continuity of service is absolutely essential, and shutting down the system is completely impractical.
Give me an example of when that would be justified.
Well, imagine you're dealing with a continuous chemical reaction in a petrochemical refinery. Shutting down a main feeder line might cause miles of product to solidify inside the pipes, which would destroy the facility's infrastructure.
Oh, wow.
Or you might be tapping into a municipal water main supplying a hospital network, where cutting the pressure poses a massive public health risk.
Okay, so because energy isolation is impossible during a hot tap, the safety equivalency must be achieved through unparalleled engineering controls and specialized procedures.
Yes. The process is fascinating. It involves welding a specialized fitting onto the live pipe, bolting a full port gate valve to that fitting, and then bolting a hot tap drilling machine to the open valve.
And then the drill bit literally passes through the open valve, cuts a coupon out of the live pressurized pipe, retracts back through the valve, and the valve is closed to seal the new connection.
Exactly. The technicians rely entirely on the structural integrity of this specialized tapping machine to contain the pressure during the cut.
The level of documented procedural oversight, ultrasonic thickness testing of the pipe wall before welding, and the specialized operator training required for a hot tap, it just goes far beyond standard LOTO practices.
Because it is a highly calculated manipulation of active energy rather than an isolation of it.
In complex scenarios like hot tapping really illustrate why Domain 2, Topic 6 has to be viewed within the broader context of the hierarchy of hazard controls, which is covered in Domain 2, Topic 2 of the ASP blueprint.
Exactly. Because lockout, tagout fundamentally is an administrative control. It relies on policies, procedures, and human compliance to apply a piece of physical hardware.
And administrative controls are lower on the hierarchy because they are vulnerable to human error. Elimination, substitution, and engineering controls offer superior protection because they remove the hazard from the equation entirely, or physically prevent access to it regardless of human behavior.
Yes. And this is where we integrate the standards established by Underwriters Laboratories, or UL, and FM Global, which are also referenced in our study texts.
Right. UL 508A sets the rigorous safety criteria for industrial control panels, dictating the layout, wiring, and insulation requirements.
And FM Global provides stringent guidelines for machine guarding and property loss prevention.
So a facility can proactively use these engineering standards to design machines that are inherently safer to lock out from the start.
Exactly. Instead of requiring a technician to track down 5 different pneumatic valves and 3 electrical disconnects scattered across a factory floor, the equipment can be engineered with a centralized, interlocked energy isolation manifold.
Oh, that makes it so much easier. And engineering controls can be integrated directly into the machine's architecture, too.
Right. Rather than relying on a technician to manually insert a heavy, cumbersome die prop into a stamping press, the press can be designed with automated permanent safety blocks that physically deploy into the crush zone the moment the access doors are opened.
So by engineering the physical barrier right into the operational sequence, you drastically reduce the reliance on the flawless execution of an administrative LO procedure.
Yes. The ultimate goal for a safety professional isn't just to write a compliant Lockout Tagout program. It is to advocate for capital investments in engineering controls that make the administrative LO program as streamlined, intuitive, and error-proof as physically possible.
Which is brilliant, because when you synthesize electrical principles, fluid dynamics, human performance psychology, and structural engineering, you elevate your practice from simply enforcing regulations to actively designing safer work environments.
Exactly.
Well, we have mapped out a massive amount of technical and procedural terrain today. Let's distill the core architectural principles of hazardous energy control for everyone tuning in.
Sounds good.
First, we must respect the invisible threats. Hazardous energy is a multidisciplinary spectrum. It is the compressibility of pneumatic air, the latent heat in a boiler, the residual magnetism in a massive rotor, and the trapped pressure in a hydraulic accumulator. If it has mass, movement, heat, or pressure, it must be aggressively managed.
Right. Second, the written program is the facility's operating code. It cannot be generic. Every piece of equipment demands a highly specific, documented sequence for shutting down, isolating, blocking, securing, and transferring control.
Third, the verification step tryout is the ultimate safeguard. You must attempt to operate the equipment or utilize a multimeter via the 3-point test to physically prove the isolation was successful before exposing your body to the hazard.
Absolutely. Fourth, we must honor the supremacy of physics over software. Energy isolating devices mandate a physical, mechanical separation of the energy pathway. Emergency stops, selector switches, and PLCs are fragile control circuits that offer no mechanical guarantee against an unexpected startup.
Fifth, tagout is an administrative illusion of security, permitted primarily for legacy equipment. It provides zero physical restraint and demands flawless behavioral compliance to achieve an equivalent level of safety to a physical padlock.
Sixth, cognitive biases must be managed through role separation. Authorized employees execute the isolation with deep technical knowledge. Affected employees must view the lockout devices as absolute, impenetrable boundaries.
And finally, the normalization of deviance must be combated through mandatory annual peer review. The other than rule ensures an independent set of eyes verifies both the technician's execution and the accuracy of the written procedure itself.
Understanding those core principles is the key to mastering this section of the ASP blueprint. But beyond the exam, applying these principles with uncompromising rigor is how safety professionals ensure that the men and women conducting high-risk maintenance operations return home intact at the end of every single shift.
That is the definitive bottom line right there. But before we wrap up our discussion today, when we close out this session of QHSE Talks, I want to leave you with a conceptual challenge regarding the future of energy isolation.
Okay, let's hear it.
We have spent our time discussing mechanical disconnects, physical padlocks, and human behavioral controls based on the industrial architecture of the late 20th century. But manufacturing is undergoing a radical evolution.
Oh, for sure.
We're deploying advanced autonomous robotics, highly integrated predictive maintenance software, and systems equipped with internal kinetic energy recovery networks and massive lithium-ion battery backups.
Yeah, the landscape is changing fast.
So in a near-future facility where a machine runs its own diagnostic algorithms, draws power from an internal distributed microgrid, and physically repositions its own robotic arms to optimize workflow. The concept of a single main breaker becomes obsolete.
That's a scary thought, but it's true.
How will the analog, physical constraint of the padlock evolve to effectively isolate systems that are designed to be entirely decentralized, predictive, and autonomous? When the machine possesses its own internal logic and localized energy reserves, how do we definitively guarantee it remains dead while a human is inside the operating envelope?
Wow. It is the next great frontier in safety engineering, requiring a complete reimagining of physical interlocks and firmware-level energy suppression. The safety professionals entering the field today will be the ones tasked with writing the standards for that autonomous future.
It's a massive challenge for the next generation's engineers to tackle. Thank you for joining us for this extensive session of QHSE Talks. Keep analyzing the systems around you, trust the physics, and above all, stay safe out there.